Section 8.3 goes into more details about an equivalence relation. Now, I've already defined an equivalence relation as any relation that has the three properties of reflexive, symmetric, and transitive. What they do in your text is they examine a bunch of systems that will have these kinds of properties. One of the very first things they do, and I'm not going to stress, is the idea of a relation induced by a partition. They just very generally say that you can go in and partition any set. And when you partition it in any of these ways, it's going to give you an equivalence relation. We already examined a couple of important examples of equivalence relations. Well, we didn't really talk about them that way before. For example, we did the congruence mod 2 relation, which partitions the integers into evens and odds. Remember, this is a partition because if I do the union of the evens and the odds, I get all of the integers, and they are non-overlapping. There is no intersection between the evens and the odds. Let's look at this a little different way. If I were to put all these numbers infinitely out here, all of the integers, obviously I can't do that. If I were going to try to do a directed graph on this, every one of these things would E itself, using that E definition we did before. If I wanted to look at the other numbers that are going to E0, 0 is going to E2, 0 is going to E4, 0 is going to E a negative 2, 0 is going to E a negative 4. And it goes the other way, which shows that we have symmetry. And we'll have to do that for every one of these things because, 4 is going to E this, and this is going to E this. And likewise, negative 4 is going to E negative 4, and negative 4 is going to E 2, and 2 is going to E negative 2. So we get a diagram that looks kind of like this. So it's getting, with this piece of it, to have all the right properties. And you'll notice negative 1. If we go the other way, looking at the things that are all of the odds, we get this relationship. And indeed, if you were kind of trying to draw this out, it has all three properties. So congruence mod 2, partitioning the integers into the evens and odds, is an equivalence relation, which leads us to another term that's in section 8.3, and that's the idea of a class. Here I have evens, here I have odds. What I could do is select any element in here, like 0, and any element in here, such as 1, and talk about this as being the class of 0, and this being the class of 1. That 0 or 1 is acting as a representative or prototype of all of the elements that are in that collection. We use the word class here much in the same way as you talk about a class of a ship. If you talk about a class of aircraft carriers or of nuclear submarines, you say all the nuclear submarines are of the Ohio class. You're talking about all the submarines that have the basic weight, size, shapes, and capacities as an Ohio class sub. And this is really where the word class comes from in computer science. When you are when you're doing object-oriented programming, you make classes with properties of things, and when you say something is of a certain class, it has all those properties. Well, this is where that whole idea is coming from. Well, this also works for what we did with congruence mod 3. When we did congruence mod 3, we partitioned the integers into 3 sets. The set of multiples of 3, the multiples of 3 plus 1, the multiples of 3 plus 2. So it's a partition because the union of these 3 sets gives us all of the integers, and the intersection in any 2 of these sets is going to be null. They are not overlapping. We could choose 0 here, 1 here, and 2 here as prototypes. Of course, it would be just as legal, but probably wouldn't be as effective, to say it's of the class 5. But here we have 3 classes. Just to see something, notice that if I wrote this in terms of classes, everything in this class relates to itself. And what you have is an equivalence relation. Now, a really interesting thing with this is they go to the point in your text in section 8.1 at looking at congruence mod anything, mod 7, mod 6, mod 20, and they do a proof that shows all of them are equivalence relations. And that's an important thing to know. It'll save you a lot of time when you start answering questions about things. What you do, and a lot of times in mathematics, is you'll notice that something is an equivalence relation, and once you know it's an equivalence relation, you know it has all of those properties. The other thing that they'll do in this section of your text that I'm not going to emphasize so much, but I think it's an interesting property, is that if you go back and look at all of the sets that you worked with the digital logical circuits, well, these things also make up equivalence classes. You might like to read through some of that to see it's the same kind of thing, and that the equivalence classes would say, since this circuit and this circuit have the same truth table, that means they are equivalent circuits, and we'll now say that they are elements of the same equivalence class.